Hello, student. Welcome to the statistical mechanics. And in this class, I am going to derive an expression for Maxwell Boltzmann distribution. So in the last class, we have compared all these three distributions, and now we are going to uh, derive the expression for distribution function in each case. So I am concentrating on this Maxwell Boltzmann distribution, and you have to write the characteristics of this Maxwell distribution uh, in the examination before starting up the derivation. So the characteristics of the Maxwell Boltzmann distribution are: the particles are identical but distinguishable. So this is very important. The particles are identical but they are distinguishable. And a state can be occupied by any number of particles. That is the second point. And the spin of the particles is not taken into account. So whether the particle is having spin or it don't have the spin, no matter. Simply we will count the particles. Next, examples are: a system of gas particles is the best example for the Maxwell Boltzmann distribution, and the internal energy of absolute zero is taken as zero. That means when the system is at absolute zero, in this case, its energy is taken as a zero, and it obeys the classical laws, don't obeys the quantum mechanical laws, and the the most probable distribution is given by this equation. This we have to derive at the end of the session, and these are called as the classical particles. So these are the characteristics of the Maxwell Boltzmann distribution, and we will start the derivation. So this is the derivation part. Consider consider a system of n, capital N, number of identical particles like gas particles, and let these particles are grouped like this: n1, comma n2, comma n3 dash dash ni are the group of particles having constant energies E1, E2, E3 dash 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 ei respectively. That means whatever the number of particles are there in the group n1, all will be having the constant energy of E1. This is the meaning. Next, the total number of particles is capital N, that is equal to sum of all these. So it is n1 plus n2 plus n3 dash 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 plus ni, and this is equal to constant. And the total number of particles is not going to change. It is a closed system. Next, the total energy of the particles Et is written in this way: E1 N1 E2 N2 dash 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 Ei Ni is equal to constant. As I told, this N1 itself is a group of particles, but all particles are having constant energy of E1. So therefore, this is multiplied to this group number. And next, therefore, equations 1 and 2 can be written using the and they are differentiated actually. They are written in the short form, then differentiated, then it becomes dn. Actually, n is equal to summation over I ni. Equation 1 can be written as n is equal to summation over I ni. But at the same time, I am differentiating that equation, so that this becomes dn is equal to summation over I dni is equal to 0. Similarly, the second equation, that is et is equal to summation over I ei dni is equal to 0, and this we are not going to differentiate because this is a constant, therefore it is kept as it is, and only ni is differentiated, so that becomes a dni. When the gas is in thermal equilibrium, the probability will be maximum. And according to Boltzmann entropy relation, S is equal to K log omega, or S by K is equal to log omega. And in here, this S is the entropy, and K is the Boltzmann constant, and omega is the probability. Probability means probability of occupancy of the states by the particles. Next, the probability of occupancy of G1, G2, dash 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 Gi states by N1, N2, dash dash Ni number of particles is given by omega is equal to product over I, Gi raised to Ni divided by Ni factorial. So this to get this equation we have to work out little bit. And here what we are doing, the particles are distinguishable, and there are the Gi number of states and Ni number of particles are there. By using permutation and combination, we have to distribute these particles in these states. So at the end, we are getting this equation. So this is the product symbol, not the pi symbol. It is the product. The meaning of this symbol is here. It is a product. Then taking a log on equation 6. So this becomes log omega. Log omega is equal to log of this quantity. Log of this quantity. And this is equal to, here when this log operates on a product, it becomes sum. So summation over I, log of Gi raised to Ni divided by Ni factorial. And we'll simplify this one. This is equal to summation over I, and this log of Gi raised to Ni is written as Ni log Gi using the logarithmic rules, and minus log of Ni factorial, because two logarithmic formulas are used here. Log of x raised to n is equal to n log x is the one formula which is used here, and another logarithmic formula is log of a by b. Log of a by b is log a minus log b. So these are the two relations used um, in this equation, and this is equal to summation over I, and ni log of Gi, Ni log of Gi minus Ni log Ni factorial is written as Ni log Ni minus Ni. So this is written using the Stirling's approximation. So the Stirling's approximation is like this. So log of Ni factorial is equal to Ni log Ni minus Ni is the Stirling's approximation, and that I have used. Next, go on simplifying. So this is equal to summation over I Ni log Gi minus, so this I wrote using Stirling's approximation. Then I will simplify this one. So this becomes Ni log Gi, and multiply this minus sign to this bracket, it becomes minus Ni log Ni plus Ni. So this is the equation 7. And next we have to differentiate equation 7. What happens you see? So that I will write as d log omega. D represents the differentiation. So d log omega is equal to summation over I dni log Gi. So here I actually, in the equation 7, the first term is there, Ni log Gi is there. This is to be differentiated, and the Ni and the log Gi, these are the two terms, and it is in the product form. So you have to use the product rule for the differentiation. So product rule is used here. So Ni is differentiated, it is dni log Gi is written as it is, plus Ni is written as it is, and we are differentiating log Gi into dgi. Next, we are moving to the next term. So we have to differentiate ni log ni. Again, it is in the product form. So minus ni, differentiation of log ni is 1 by ni into here also, sorry, this is also 1 by 1 over gi into dgi, because log of gi is 1 over gi into dgi. Just make it corrected. And here minus ni into log of ni is there. Differentiation of that is 1 by ni into dni, minus differentiation of ni is dni, and log ni is kept as it is, and last term plus ni is there, its differentiation is dni. So here ni get cancelled, and dni get cancelled, and we have written the remaining terms here. So this is d log omega is equal to summation over I, and here dni log gi is left here, and this term goes to 0 because this gi is constant, so dgi is 0, and we are left with this term and this term. So it is dni log gi minus dni log ni, or this is equal to summation over I. Dni is common, it is written, it is taken out, and log gi minus log ni is written as log of gi by ni using the logarithmic rules. So let this is the equation 8. Then in the steady state, omega is a constant, probability is a constant, and hence d log omega is equal to 0. So therefore equation 8 becomes, equation 8 is here. So I will keep I will make this 0, and this becomes equal to 0. Therefore summation over I dni log of gi by ni is equal to 0. So this is the equation 9. Next, multiply summation over I dni by alpha, and summation over I ei into dni by beta, and subtracting from equation 9, where these alpha and beta are the constants to be determined. So the equation 9 becomes, summation over I dni log of gi by ni is there, and this thing minus summation over I dni alpha, because summation over dni is multiplied by alpha and it is subtracted, so this term, and similarly this term, so that is minus summation over I ei dni into beta is equal to 0. Next, summation over dni, summation over I dni is common, which is present in all the terms, and take it common and send to the RHS, it becomes 0, and the remaining terms are log gi by ni minus alpha minus beta ei is equal to 0, or log of gi by ni is equal to, taking these two terms to the RHS side, it is equal to alpha plus beta ei, or gi by ni is equal to e to the power alpha plus beta, because we are removing the log this side, see the other side goes exponential, so therefore gi by ni is equal to e to the power alpha plus beta into ei, or rearranging the terms, this equation can be written as ni is equal to, take ni to RHS and take this to LHS, so it becomes ni is equal to gi divided by e to the power alpha plus beta ei. So in this way we got an expression for distribution function of the Maxwell Boltzmann distribution in this week. So this is a very important relation, will be asked in the examination directly to derive it. So thanks for listening.